I'm Mary McGlohon. I work at Google and have been working on SRE for ML specifically for the last 6 years. In my past life, I had worked as a machine learning researcher, and then after my thesis was done, I was like, well, that's enough of that. Never thinking about machine learning again. Went to Google, like let's just write some code. Found myself in SRE. And now I found myself again working on ML systems, and I'm especially excited. It's actually been an interesting turn because now, especially with some of these more generative AI applications, the research is getting a lot closer to production. Like normally we would have seen like research is happening, and then eventually we iterated on enough that we can put it into production. But that cycle seems to be getting a lot faster. And it's been interesting for me because I thought I was safe and didn't ever have to think about machine learning research again, but here I am. Yeah. So I'm especially interested in some of the data reliability problems because so much of ML is about data. They're very interesting systems and ways to optimize things. And so ML is doing more and more sophisticated things, and it's also becoming more accessible. 2 years ago, I gave a talk here called "Demystifying ML in Production," and I had said at the time, well, yeah, machine learning is starting to be everywhere, and in the last 2 years, that has gotten even more the case. Machine learning is now being used for lots of things that are very close to the user: language summarization and generation. There's code generation, and these language models can even be used for other kinds of languages, such as for like DNA for drug discovery. And this matters because the newer AI it has this emergent behavior, and that means that the inputs are starting to matter even more. In typical software, you're writing code, and then you're executing that code. But in machine learning, the code is being written for you, and then it's executing on this thing that's being generated by a different process. It's a lot harder to observe, and the inputs that you're giving it tend to matter more because the inputs are eventually becoming part of the code that you're generating. And this can start to impact things in ways that you wouldn't necessarily expect. So we'll talk a little bit here about some of the ways to prevent and mitigate some of these failure modes. So I'll start by talking about the more familiar classic supervised machine learning models and some of their data problems as a way to compare it then to LLMs and large language models and their data problems and some of the risks that we run into, and how these can be are similar to each other and also to reliability for your non-ML systems as well. And then we're going to talk about how we can kind of help prevent and mitigate some of these bad data issues. So to talk about supervised ML. So in your kind of classical machine learning, let's suppose that you're doing something like you're trying to optimize the content on your web page for the probability of a user to click that content. In order to do that, you have some set of features. Like you've run some metrics on your content. You say, oh, these are all the features that this content has, and then we have some results from previous logs of times when users have clicked on that content, and that you're using that labeled data. You have some ground truth of what has actually happened, and then you're trying to predict the probability that some new content will generate a click. And in the middle of that, you're doing some kind of machine learning method. Maybe it's a neural network or some kind of linear algebra in between. It may use some specialized compute hardware, but yeah, in the end, you're trying to generate an objective function. And so you do that once, but suppose you're trying to do that in production. What does that tend to look like? Well, the system is going to start with some raw data, maybe from your logs. From there, you start to generate the features for the content that you eventually want to be able to train upon. You feed that into your model training. There may be a system to do this multiple times. And then you push that trained model out into the inference step to where it's a little bit closer to the user, and then any new, you can use new content and pose it to the user accordingly. And then you have a nice online feedback loop to start the whole process over again. But your input data may be bad for some number of reasons, and Lena talked about some ways in which this happens. You may have incomplete data, you may have missing data. Perhaps some of your logs got lost, or they didn't arrive when you thought they would. Maybe something was mislabeled somehow. Maybe the click got registered as a non-click, or there was a one-off-by-one error, or your data schema changed and the seconds became milliseconds, something like that. The data could be biased. Maybe you were running some filtering on your data that over-filtered or under-filtered certain things, and so the data set that you wound up with was non-representative. Maybe your data got corrupted. Maybe you had some other process was using your data and overwrote some of it. Or maybe it was just otherwise later deemed unacceptable to use. Maybe there's some kind of there was a change in policy, a change in the way that you're wanting to handle your content, and for some reason you just do not want to train on the same data that you did before. And so that, the data isn't necessarily bad, but for your purposes it's bad, and you don't want to use it. So what does an actual ML data outage look like in this case? So what happens if you have this bad data? Maybe the data is incomplete, got corrupted, and right now it's just sitting in your storage. It's not doing any harm. It's fine. But then you start generating your features from it, and you notice that, well, we've been running some metrics on and checking what's happening with this data and the features that we're generating. It doesn't look like we expect, so we're just going to say that the feature validation has failed and we're going to halt our training. So this isn't an ideal outcome. Your training is delayed, but it's not the worst case scenario, because you're able to recover from it. You can probably go back and check what's going on and pick up your training later once you fix the problem. A slightly worse outcome is that you go ahead and train over this bad data, and then you find out that the model quality has degraded somehow, and you're able to halt it there at that point. So this isn't great, because you've then already gone through this model training, which is a pretty compute intensive process. It's also a very IO intensive process. So essentially, you've wasted a lot of compute resources to produce something that is unusable. But it's still not as bad as it could be, because the worst outcome is that you fail to catch this bad model. It goes out to production. Your predictions are bad, and your user starts to notice the problem, and that's not great, because you still have all the same problems that you had if you had caught it earlier. You still wasted all of that compute power. You still have to go back and fix the data, and it then takes longer for you to actually recover from it, because you need to then go back and retrain, and you've had this extra latency in the process. So that's what an outage looks like when it's supervised machine learning. Let's compare a little bit let's step back a little bit and compare to what happens with large language models, and talk about how these models look a little bit different from supervised ML in production. So a language model is one of the main differences is that it's unsupervised. It's just training over a text corpus of unlabeled data. There's not a particular function that has decided is the ground truth. All the data is equally considered ground truth. And the goal of a language model is just to predict the next word. The inference is say that you have a sentence, the cat climbed the such and such, and the goal of the model is to say, well, is the next token going to be sofa, or is the next token going to be tree? Is the cat climbed the tree? So that is what the language model is doing. So this doesn't sound that fancy, right? Because it's just this is why we oftentimes you'll hear on the social media they call large language models a sparkling autocorrect, because that's all it's doing. It's just completing the next word. But the thing is that it's actually very powerful, because what we're doing in the middle of it is we're training this very large model over all this text. We're spending even more compute than we were before, but the model that it's generating is actually very sophisticated. It may only be predicting the next word, but behind that, it is actually developing within its structure some of the same concepts that we have for our own human language. For instance, like it's able to classify like what internally it's beginning to understand these concepts of like classifications of different words. What's most likely to become the next word will depend on some of the internal layers of how it's structuring what it's learning. And so even though all it's doing is autocorrect, it can serve as a building block for doing a lot of other things as well. So what we're doing here is in this building block is what we call pre-training, and that's then used to generate a lot of other models. But to actually generate this, we do a step called fine-tuning. That's taking this pre-trained large language model and then also generating some kind of high-quality data to specialize it for a particular purpose. Say that you want to take this language model and modify it to do document summarization, for instance. You can then take some labeled data, probably from human raters, but it could be from other sources as well. Feed that into the model training, and what you end up with is this fine-tuned model for a particular purpose. And you can then use that same pre-trained model for a different purpose as well, using different kinds of fine-tuning. And you can go even further with this fine-tuning by having experts then train models to do reinforcement learning and have a reward function that then refines this base model even further. And there's lots of other ways for refining the pre-trained model, but essentially what we're talking about is you have this very large base model, and then a lot of fine-tuning that goes into making it usable for all these various purposes that we're seeing today. Yeah. So in production, we have the pre-training step. And then from there, we also have data sources. We have a human in the loop service that's probably being used to generate some of this high quality data that's used for the supervised portion of the fine tuning. We may have human experts that are doing further fine tuning, and then at the end you have lots of models that are being output for many different purposes. So what you'll notice about this is the way that this is going to be a little bit different from supervised machine learning is one thing is the scale. You have a much larger model training system. You have much larger storage that you're going to need for storing these trained models. Then that storage needs to be available for all the fine tuning that you're going to do on it. And then you also notice that this is a much more complex process. It isn't just a one automated process in a loop. You have human operators that are working with things. You have these varied kinds of services that you're using. Like the service that you're using for human labeled data is a lot different from the kind of pipeline service that you're going to be using for a supervised process, for an end-to-end supervised process. And it's going to look a lot different from the pre-training as well. And there's also just a lot of entry points of data, and so a lot of ways that things can go wrong. And of course, there's going to be wide impact as well. So what are some of the things that can go wrong? Well, when we're talking about the pre-training step, we're working with a lot of unstructured dynamic data, and that makes it a little bit more difficult to instrument the kinds of metrics that you might be doing over a more standard supervised process. There's going to be some inherent bias in the data because you're using an entire corpus, and you aren't necessarily knowing what exactly unbiased data looks like. This data may also be of unknown origin. There may be some data within there that may be AI generated, and you may not have a way of detecting that. The data may be too large to multi-home. So when you're running into the problems of having missing data, you may not be able to know if it's missing or not because you don't have another replica that you can look at. And of course, there's going to be usage requirements similarly to what we would have in other machine learning problems as well. But since the data is unstructured and dynamic, it's a little bit more complex to monitor for these things. The other difference that you run into with pre-training is that the model training being so much larger means that you have very high bandwidth that's required to train. So it's very high wastage if the training goes wrong. You can also run into the case where data can become accidentally dropped because you're working at this kind of scale. And finally, once you do have this pre-trained model, then if something is bad there, then that means that all of these downstream dependencies are also going to have problems as well. So essentially, we have kind of three ways in which the pre-training can have problems. There can be problems with input, there can be problems with cost and scale, and then there could be the problems with the downstream dependencies. So like we said, this is a fairly complex system, and you can have even more entry points of issues that come in with this fine-tuning. And so one of the things to note when you're doing this fine-tuning with human-labeled data is that it's really about the quality of the data that matters. If you're already using a base model that's training over a huge text corpus, quantity is not going to be the issue that you're running into. You've already gotten that with your base model, and so what really matters is making sure that the fine-tuning data sets are of high quality. That is actually more important than having a lot of data. There's also, so in order to ensure that quality, it's a little bit tricky to know what quality means, because if you're using human-labeled data, then humans are subjective. Like why is this rater's opinion better than that rater's opinion? So there's challenges in tracking and consistency here. These rating tasks also need to work in a dynamic system, which is much harder to scale than a standard data pipeline, because you have different kind of latency and availability needs. You have more various ways that humans are interacting with the system, and the tasks also need to change pretty often. So, for instance, if you're training different kinds of models for different kinds of purposes, maybe the requester for this data needs to have their own code running in order to do that. And so that's a lot harder to keep stable as you're introducing more and more variables into this service. So there's also a high cost to evaluating the model once you have done this fine tuning, because the objective function of what we want the model to look like in the end is going to be more ambiguous. And so then you have all these systems that you're trying to monitor in sequence. So if you do run into a problem, what does it actually look like? So just as an example, if we have some data that is bad in your text corpus, what is the impact of that? Well, once you have this very, very expensive wasted compute, you end up with a bad base model, and then as you go into fine tuning, you have all these unusable fine-tuned models because they're all based on this data that was not really meant to. That was not good. So what do we do about that? It turns out that we can use many of the same SRE practices that we're familiar with. Like, it all comes down to a lot of the same things: doing testing, monitoring, documenting, and having some good mitigations. So the first recommendation we have is that you want to trace the lineage of both your data and your models throughout the model journey. So for instance, if you just detect a problem via fine-tuning, which is one thing that fine-tuning can be good for, is that if you have humans who are actually interacting with this model, you'll be able to detect a problem more quickly. But the problem is once you've done that, how do you know what the source of the problem is? And the only way you can really know the source is if you have an understanding of, for instance, what was the base model that is being trained on? Are you tracking that? Which version of it is it? Which data sources went into that model? You need to be able to trace upstream to actually find where the issue was, so that you can recover it and improve things. You also need to be able to trace forwards. Once you know that the base model was bad, you need to know all of the fine-tuned models that were trained on that model, and be able to pull those back as well. So it's pretty critical to have an understanding of what the lineage and what the model provenance is. This is necessary for any ML model, but it's more important for LLMs because of this higher complexity. It's just more likely that something's going to go wrong along the way, and the impact is much wider, especially in the case of the pre-trained model. So how might we like to do that? Well, since as we said, we have all these very complex systems, and they don't look alike. So it's a little bit difficult to actually instrument the same metadata tracking in order to track this lineage and store it within, for instance, your base data storage, or even within the fine-tuning data storage. So you may have you're going to have different requirements for storing this metadata, because many different operators are going to be working with it. You want to be able to, as for instance, an ML ops person, be able to say, okay, well, I know that this model is bad. I need to easily query this one system that can tell me everything that's traced to it. And so you probably want an independent storage for your metadata that is not the same as where you're storing your models or where you're storing your data. But this is hard to do, because even if we do have our own independent system for it, you're dealing with lots of different kinds of data that may be stored here. And you have many different systems that need to instrument this tracking. And of course, you need to get consensus then on what metadata actually does need to be tracked. And that can be a little bit difficult, as we'll go to next. The second recommendation that we have is to ensure agreement between the data producers and the data consumers throughout this entire process for your data integrity requirements. When you have so many parties that are consuming this data or the models as data, you have a complex system. There are many interdependencies here, and you can't rely on assumptions. You've seen this for even your most basic data integrity problem. People need to agree on how to escalate when there is a problem, and that isn't always easy to do. And so when it comes to this even more fine-grained things, then it becomes even more important to make sure that people understand where the data is coming from, what it's meant to be used for. Because if it's misinterpreted between the steps, then you can get inaccurate results, and data that is being misused is bad data. So, for example, some of the things that you may want to make sure that people agree on: where the data is stored. In some cases, especially for pre-training, you probably want to have your data input data be stored close to where that training is happening, so that you can avoid super high bandwidth costs. You also need to be clear on what data is actually valid. Is the data ready to be trained on, or does there need to be cleaning that happens before that? When do you know that it's ready? You need to be clear on what are the availability and recovery objectives. If data does go missing, how do you inform people of that it's missing? How can people inform you if there's a problem? And how quickly can you recover? And what is needed to recover? You need to agree on what data and model metadata needs to be tracked. If there's validations that need to run, which validations do actually exist, and what do they actually mean to people who are using these models? People need to be clear on what the data usage requirements are, who is allowed to use it, what models can run on it, and what are the limitations of the data. What input data is writable? Is the data meant to be used once? Are there processes that can run on it to refine it? And because this is going to be very different depending on the kind of task that the kind of training task that you're doing. What are the requirements for data labeling, and how do you then interpret this labeled data? And finally, how to handle shared data, including the shared models. And so anybody who's working along this process needs to know what the requirements are. And so so this is pretty complex, and you have a lot of roles involved. That's what makes it difficult, because people may have different opinions on what's the best way to do things. And you have a lot of people working along the way. You have a model researcher who may have a high priority on very quickly being able to iterate on experiments. You have a system engineer who's just going to say, I would like people to never change, and I would like this system to stay stable, and I do not want any development velocity at all. If they're being really cranky about things. You have all the humans in the loop who are working on writing prompts, who are labeling data, and who have a fairly close understanding of how these models are working, and their input needs to be included in the process as well. Otherwise, your model quality is going to suffer. And so and all these parties have different requirements, and you may not have just one storage system that will work for everything. And there might be differences for the data that goes in, and then how the model interprets it. Like skew is still going to happen even when you get all the people to agree. So, given that like even our best efforts are likely to fail, what do we do? The third recommendation that we have is to make rollouts safe as possible and to make rollback easy. So as we said, detecting the model quality outages before they're widely visible is always best. It's even better if you can detect the data quality issues before you train this super expensive model. But if something does go wrong, you do want to be able to detect it and then recover quickly. And as everybody in the audience is aware, the safe rollouts and easy rollbacks are not something that's specific to ML. So what are the techniques we would use here? These are all should be pretty familiar. There's using gradual rollouts with canarying, having reliable storage for your snapshots and versions, so that if something does go wrong, that you can quickly get the old model version and use that instead. Make sure that your rollback procedures are tested well, especially every time there's a very large change to the system and the way that your data is moving through the system. You want to make sure that you that your rollback procedures will actually work for any of the changes that had happened in the meantime. Retain the old model versions, know what's needed to recover, and then once you do detect a problem, have the ability to then exclude that data and then before you retrain, and that'll help to make your time to recovery much faster. But this is hard. This is hard with LLMs. There are challenges in scale. There's for instance, if the model is so large, then you cannot necessarily easily swap it out within minutes. It may take much longer to quickly change the versions for your canarying or in the case of outages. You may also run into problems with backwards compatibility. When there are like fundamental changes to how the model operates, then it may not be easy to roll back, and you need to know how what are some of the other variables that you may need to tweak in order to have a successful rollback. And if a rollback isn't possible, you need to know how to mitigate that. And finally, knowing when to roll back really depends on how good your lineage tracking is to begin with. If you're not able to, you can't. It doesn't matter if you can exclude the data from training if you don't even know what the data is that you need to exclude. Yeah. So in conclusion, we found that LLM data reliability may look similar to reliability for other services, but it's much more expensive if you get it wrong. And so we've highlighted three recommendations and ways of thinking about this. One has to do with lineage tracking. We've highlighted the importance of instrumenting this monitoring end-to-end to surface some of these more difficult to detect failures. We've highlighted the importance of creating consensus among all the data producers and consumers and ensuring that your human communication paths are working well. And finally, we've highlighted the importance of limiting your blast radius and knowing how to recover using safe data and model rollouts and rollbacks. So, thank you very much.